Hi everyone, in this we will learn how to design a frequency divided by 3 using D flip-flops. Unlike a divide by 2 circuit, generating a divide by 3 signal with a 50% duty cycle is not straightforward because the division factor is odd here. We will first build mod 3 counter and then use an additional D flip-flop to generate a perfectly symmetrical output waveform. First, let's understand the mod 3 counter. This circuit consists of two D flip-flops. Both flip-flops are configured in toggle mode by connecting the complement output Q bar back to the input. The first flip-flop receives the external clock directly, and the output of the first flip-flop is connected to the clock input of the second flip-flop. Since the second flip-flop is clocked by the output of the first flip-flop rather than the main clock, these flip-flops operate asynchronously. The additional logic here, consisting of an AND gate, monitors the counter state. When the count reaches 3, the AND gate activates the clear input, resetting both flip-flops back to 0. This is why the circuit is called mod 3 counter. Now let's use this mod 3 counter to generate a divide by 3 clock. The output of the mod 3 counter already repeats once every 3 input clock cycle. However, the duty cycle is not 50%. The high and low duration are unequal. To correct this, we add one more negative age trigger D flip-flop. Notice that this flip-flop is clocked by the same input clock. Its D input is driven by the output of the mod 3 counter. Because this flip-flop updates only on the falling edge of the input clock, the output becomes a delayed version of the mod 3 counter output. The delay introduced is exactly half of one clock period, or T by 2. So now we have two signals, the original mod 3 counter output and the same signal delayed by T by 2. Finally, these two signals are combined using an OR gate. The OR operation merges the original signal with its delayed version. As a result, the high interval is extended. The output now remains high for 3T by 2. Similarly, the low interval also becomes 3T by 2. Therefore, one complete output cycle is 3T, which means the output frequency is input frequency divided by 3. At the same time, the high time and low time are equal, giving a 50% duty cycle. This is the key advantage of adding the negative age trigger D flip-flop and the OR gate. Let's verify this using the timing diagram. The top waveform is the input clock. Below it is the output of the mod 3 counter. Notice that this signal does not have a 50% duty cycle. Next is the output of the negative age trigger D flip-flop. It is simply the mod 3 counter output delayed by half a clock period. Finally, the OR gate combines these two signals. The resulting waveform stays high for 3T by 2 and low for 3T by 2. The complete period is 3T, confirming that the output frequency is exactly 1/3 of the input frequency while maintaining a 50% duty cycle. So to summarize, we first built a mod 3 asynchronous counter using two D flip-flop operating in toggle mode. Then we sampled the counter output using a negative age trigger D flip-flop, introducing a delay of T by 2. Finally, by performing an OR operation on the original and delayed signals, we obtained a divide by 3 output with an exact 50% duty cycle. This technique is widely used whenever an odd frequency division with a symmetrical clock waveform is required. Thank you for watching and see you in the next video.